So welcome. We're going to talk about SPDY and HTTP2. All the slides and links for this talk are available at this short URL. And hopefully that's the last time I'm going to say HTTP2 because it's been decided we can simply say H2 to save us all a little bit of pain. So I'm going to say that going forward. All of the figures from this book, or from this talk, come from this book, which is a great book if you like kind of networking stuff, if you like the low-level deep dive into the networking layers. I would highly recommend picking up a copy. Bit about me. So I was formerly a performance engineer at Etsy. I started the Boston Web Perf meetup group. As of a couple weeks ago, I'm a former CTO at a pre-product startup in Boston. We never launched. We actually failed a couple weeks ago, unfortunately. But the takeaway there is that we were planning on launching with HTTPS everywhere and H2 support. And my goal today is to convince you to do the same. So the first step in demystifying SPDY and H2 is to explain the difference between them. Essentially, SPDY was an experimental protocol developed at Google. And then H2 is the official second major version of HTTP based on SPDY. So H2 was a reaction to the work being done at Google on SPDY. They wanted to standardize it, make it official, so we could deploy it more widely. If you think about the future of these two protocols, so H2 was approved by the IETF for publication as a standards track RFC. We'll talk about what that means in a minute. And then Chrome is removing SPDY support in 2016. So SPDY will be deprecated. It's going to get pulled out of all the browsers, and then H2 is the future. I'm going to try to say H2 consistently throughout the rest of the talk, but if I accidentally say SPDY, just realize I'm going to use them interchangeably going forward. Another way to look at it, from Mark Nottingham's blog, he says H2 is done. What does this mean? Well, he's currently the chair of the IETF HTTP working group, so he knows what he's talking about. The way to think about this is the spec is finalized. You can work on it today. You can deploy it today. Support is very, very good when it comes to browsers. The latest version of all major browsers supports H2, which means that the global support is around 80% today. I'm opening with this because I want to emphasize that everything in this talk is widely applicable right now. You may have noticed that IE 11 has partial support. What this means simply is that H2 is supported on Windows 8 and later in IE 11, but it is not supported on Windows 7. All right, let's get into the details. To talk about HTTP, we first need to understand where it fits in the network model. HTTP is an application layer protocol, which is the highest in the stack. And this model is why people will often say things like HTTP sits on top of TCP. To deliver the best possible experience to your end users, you need to have a basic understanding of both TCP and HTTP. So we're going to talk about both of those protocols today. And since HTTP is the higher layer, we're going to talk about TCP first, so you understand the baseline of how HTTP uses the TCP connection that it sits on top of. When you talk about TCP, you're going to see the ubiquitous time sequence diagram. How many folks have seen this kind of thing before? All right, that's about half the room, so we'll go through this pretty quickly. So sender on the left, receiver on the right, time flowing down the page. Through a handshake, there's a SYN packet from the sender. The receiver responds with SYN ACK, and then the sender acks that SYN and sends the first packet of data, which is typically an HTTP request on the web, right? This first segment, this first SYN ACK is one round trip. And in this particular example, it's 28 milliseconds. This is a measurement of the latency between the sender and the receiver, and it's the cost you have to pay before you can send actual data. Let's do this in a real example. So here's the US. It's not too bad, right? There's fast, light is fast. So let's imagine we're sending a packet from where we are now in SF to my hometown of Boston, Massachusetts. This is about 2,700 miles one way. The speed of light is 186,000 miles per second. So you might naively assume the round trip time, if you do the math, is going to be somewhere in the neighborhood of 28 milliseconds. How many of you think this round trip is going to take around 28 milliseconds? OK, nobody. How about around 50 milliseconds, twice as much time? Anybody think that? A couple people. What about around 75, 3 times the time? All right, 3 or 4. So most of you guys think longer, around 100 milliseconds maybe? OK, people are a little hesitant to put their hand up. But the actual round trip time is going to hover around 75 milliseconds for this. And this is actually global ping statistics. I'm guessing this is data center to data center. This is probably not measuring last mile latency. So 75 ms from SF to Boston is a pretty good round trip time. Probably going to see something worse than this in the real world. Now, why is this? Well, there's a few reasons, right? The speed of light in fiber is about 35% slower than the speed of light in air. Network equipment adds some small delays. We're not taking direct path. So there's all those things that add latency to the connection. And it gets worse because of something called TCP slow start. How many of you guys know what this is? OK, only like a couple people, so this is great. To look at this in a time sequence diagram, you can see our three-way handshake at the top, which we talked about. Then there's some server processing time. And in this particular example, we're starting with an initial congestion window of 4 packets. What this means is that the receiver is only going to send 4 packets of data in the first round trip, and then the sender has to act those 4, and then it'll send 8. The sender has to act those 8, and then it'll send 16. In this particular example, you can see that last segment's only 3, because this example is imagining there are fewer than 16 additional packets to send. The point of this algorithm is to avoid network congestion. Essentially what it does is it limits the number of packets that are in flight. And it increases that number exponentially until it sees packet loss, and then it backs off. The goal is to avoid flooding the network with packets and causing a condition called congestion collapse, where there are so many drop packets in the network and retransmits that the conditions of the network are degraded. Now, this isn't just theoretical. This was actually observed. There was an RFC that investigated this condition, and it says the condition of congestion collapse is stable. Once the saturation point has been reached, if the algorithm for selecting packets to be dropped is fair, the network will continue to operate in a degraded condition. And like I said, this was observed in the early internet in October of 1986. And as a result, we have slow start, which is deployed almost everywhere. Now, the way to think about congestion collapse is pretty simple. Think about a traffic jam on the highway. If you have cars still entering the highway from the on-ramp, the traffic jam is never going to let up because you're still shoving cars onto a full interstate. So this is congestion collapse. It's a stable condition. Things are still just screwed forever. So how does this impact our network throughput? This is a graph of congestion window size as a function of sort of round trips on the network. So you can see there's an exponential growth phase where you start with 4 packets, or in most cases today, a 10-packet initial congestion window. Then it's going to double and grow exponentially until you hit that middle point, which is where you see packet loss. If you see packet loss, it will multiplicatively decrease the number of packets that are being sent, and then it'll start that ramp up again. What this really means in practice is that the throughput of new connections is highly limited. If you open up a new connection, your initial throughput is going to be limited by that initial congestion window. You might think this isn't so bad, right? Because we only pay that TCP connection setup cost once per page load, right? So anybody want to hazard a guess at how many TCP connections are opened in total when you load fluentconf.com? Anybody? 50? 100? Depends on the browser. Okay. So yeah, it does depend on the browser, but this is the waterfall chart, or this is the connection view from web page test of fluentconf.com. Unfortunately, this actually is not all of them. So the people who said 100 are a little bit closer. 82 total connections are opened on fluentconf.com. Now, if you think this is a particularly bad example and it's not representative of the internet as a whole, let's look at a highly optimized page. So this is youtube.com, which is actually the highest traffic site on the internet that actually has real content on the homepage. Google and Facebook get more traffic, but their homepages are pretty bare and bones if you're signed out. So even YouTube, which is super optimized, makes 30 connections on a single page load. This means 30 three-way handshakes, 30 TCP slow starts, and as you can see here by the locks on the left side, that's 30 TLS negotiations as well. And really, it's 29. You can see that first connection is a redirect from HTTP to HTTPS. And the eagle-eyed among you might have noticed that there's about 6 connections being made to each domain. What's this about? Why would a browser make 6 connections to the same domain? To understand why browsers do this, we need to talk about something called HTTP head-of-line blocking. And really, this is as simple as a single slow response on a connection is going to block all the requests behind it on the same connection. Way to think about this, let's imagine you're waiting in line at Whole Foods, ready to use Apple Pay, and the person in front of you whips out a checkbook, right? Not a good place to be. You're going to have to wait for them to finish writing their check before you can move on. So now we're kind of moving up the stack and talking about how HTTP uses the TCP connection that it sits on top of. So if we look at a typical request-response cycle in a time sequence diagram, we can see our three-way handshake, and there's this GET request sent, or 2 GET requests sent from the client there. So it's getting some HTML file, getting some CSS file. The server in those orange bars is going to do some processing, and it's going to start sending back that HTML response and that CSS response on this same connection. In this example, if the HTTP response is slow, that CSS file has to just wait, queued on the server. It can't do anything until that HTML file is fully sent back to the client. Some of you guys might be saying, what about pipelining? There's this thing called HTTP pipelining. I'm just going to quote this book directly. If the web browser is the primary delivery vehicle for your application, then we can't count on pipelining to help with performance. And if you want to learn more about this, you can read in the book, but the bottom line is, in H1 scenarios, pipelining is not really going to save you as long as you're talking about web browsers. OK, so back to our 6 connections. The idea here is you open 6 connections to the server, and it allows you to download multiple resources in parallel and mitigate some of that risk of head-of-line blocking. If one connection is blocked by a resource, you can still download other resources on those other 5 connections to that domain. The end result of this is a waterfall that's a bit steeper. So many resources are fetched in parallel, and you get that content down a little bit faster. So let's talk about these workarounds and downsides for head-of-line blocking. We've talked about multiple TCP connections. The downside here is you have extra resource utilization on both the client and the server. You're opening up these extra connections for not a whole lot of benefit. You also have bandwidth competition between those connections. You can open all the connections you want to the server, but you only have a limited amount of bandwidth. And so you're not actually going to get more throughput over the long term. You're just going to have contention between those connections once the window size is opened up. Another thing you'll see, another optimization you'll see here is domain sharding, where you have something like image1.etsystatic.com, image2.etsystatic.com, et cetera. The idea here is, again, to open up more connections. You can get 6 connections per subdomain. And so you can have 12 connections to one domain and really get things in parallel. This also has some downsides. One is you have to actually make those extra DNS lookups. And there's also some implementation complexity involved with domain sharding. So HTTP head-of-line blocking is one of the key limitations of H1 that H2 addresses. And it does this through something called H2 multiplexing. And finally, we're talking about one of the main benefits of HTTP2. Multiplexing is a pretty simple thing conceptually. Through a new binary framing layer, H2 allows you to interleave multiple requests and responses on the same connection. And the client understands how to reassemble these responses once they're received. And this completely eliminates head-of-line blocking. If we look at sort of an image of how this works, basically you have different streams that are identified in the protocol. And you can send some data from stream 1, then send some headers and some data from a different stream, stream 3, and some headers from stream 1 again. And then simultaneously, the client can be sending stuff back across the same connection. So you can imagine this as, we talked about the slow start example where you have 4 packets being sent and then 8 packets being sent. Those 8 packets could be the responses for 3 different requests, interleaved with each other. And then the client knows how to reassemble them on its side. So if you have one resource that's waiting, it doesn't have to wait anymore. Just it waits, and then everything else is sent along the same connection. So with this improvement, it really makes HTTP requests much, much cheaper. So it immediately allows us to remove a lot of optimizations we've done in the past. So you can forget about combining CSS and JS files. You don't need to inline small CSS or JS files anymore. You don't need to use image sprites. You don't want to use data URIs, which are kind of an anti-pattern now anyway. And then domain sharding becomes no longer necessary. You don't need those extra connections. You don't need those extra DNS lookups. You can completely wipe it off the map. And all of these optimizations are necessary now because these HTTP requests are so cheap in an H2 world. Some of you are probably saying, what about headers, right? So that's one of the other reasons why requests are expensive. Verbose request headers, verbose response headers are another reason why it can be extra bytes for each request, many of which are redundant. So let's see this in action. Here's a request I made for jQuery on the FluentConf website. You can see the headers, your typical GET request, URI, some host headers, cache control, user agent that's super long, et cetera. And the response headers aren't too small either, right? It's a lot of information about the response, but also some redundancy here as well. Now, this is all fine, but the problem comes when I realize I'm about to make another request for a second JS file on the page where a lot of those headers are duplicated. So let's look at this. Here's the second JS request I made on this page to lazyloadmin v3.js. And if you diff these 2 headers, you'll realize the only bytes that are different between the request 1 and request 2 are just the URI bytes. Everything else is identical in those 2 request header blocks. So this is something that H2 also wants to address. And it does this through something called HPAC. HPAC is the second major improvement to HTTP that H2 brings. And essentially, the way it works is that subsequent requests on the same connection only send the headers that have been changed since the last request, referencing headers that are the same. So you can see here we have this request header sort of key value pair. There's this static table, dynamic table thing. All that means the static table is sort of valid HTTP headers that you could see on any request. Dynamic table is something that can be generated by, like let's say you send a custom header. That'll go into that dynamic table. And then on the third section there, the encoded headers come back with just like a reference to that header that you've already sent. So on the second request, you might just say, header 2 is the same. So there's no actual content. You're just saying the second header, which in this particular example is method, it's still get. So you just send that as part of the encoded headers, and you send much, much less content. So why HPAC and not something like zlib or gzip or some other header compression method? This is basically because of the crime attack, which showed that when you use zlib and encryption, you could have session hijacking because you could sort of detect different sizes and like sort of decrypt the content based on the difference in the compressed ratios. And there's more about this in that short URL I passed around in the beginning. So HPAC was developed as a new header-specific compression algorithm. And it actually does pretty well. So here's a graph of H1 compressed size versus SPDY3 versus H2. So you can see so SPDY3, which was using zlib, does a little bit better than HPAC under H2, but they're pretty close. So especially once the number of requests goes up, it's almost at the same exact compression ratio you're getting with HPAC and with zlib. There's two other main things that H2 brings to the table as far as optimizations. Those are request prioritization and server push. Some of you guys might be thinking, well, OK, if you're sending all of the requests over one connection, you need to find a way to tell the browser these requests matter more than these requests, right? You don't want some image at the bottom of the page filling up the pipe when you need a CSS file to be downloaded so you can create the CSS object model and actually render the page the first time. I'm not going to go in depth into request prioritization because it's only a 30-minute slot, but you can imagine why that's necessary, and there's some implementation details again in the book, High Performance Browser Networking. Server push simply allows you to send resources that you know the client will need later on. This could be an asset for the next page. It could be an asset on the current page that they haven't requested yet. Now, some people get nervous about this. They say, I don't want the server pushing resources at the client that I didn't ask for. But really, this is no different than inlining content. When you inline a CSS file, when you inline an image with a data URI, you're really pushing content to the client that the client did not ask for. The server push just lets you do this while still getting the benefits of an actual request. So what are those benefits? You look at server push. These resources can be cached by the client because they're unique requests. They can also be declined by the client. So the client can say, you've tried to push this to me, but I actually don't want it. They can be multiplexed across that same connection, like everything else in H2. They can also be prioritized with that server request prioritization we talked about briefly. And then finally, if you're still worried about it, they also must obey the same origin policy. So you're not going to get a resource for a domain that you're not already connected to and already talking to. So really, server push purely provides improvements over inline content, and it has no real downsides since the client still retains all control, full control over what is accepted from the server. With all of this, the key question is HTTP2 really faster? Now, in the case of this guy's spoiler, I think probably not. In the case of H2, definitely. Some data from Google, they ran this across 4 of their main properties, and they saw a median improvement in load time anywhere from 23% to 43%, with slower connections improving even more. I also ran a test with a simple e-commerce template from a framework, and we can look at the connection view and web page test to see how this did. So this is in H1. We can see those 6 connections being made. All the resources are served from the same domain. 6 connections, and then you can see sort of the graph at the bottom where it shows bandwidth usage and then CPU usage. In the H2 world, we drop down to 1 connection. This is perfect. 1 DNS lookup, 1 TCP connection, and then 1 TLS negotiation. And then one of the more interesting things here, if you look at that bandwidth graph at the bottom, once you finish the TCP connection and once you start getting into the actual content, bandwidth usage gets pretty high quickly and then stays high throughout the rest of the page load. If we look back here, you can see some dips. Maybe that's JavaScript execution. Maybe it's something else going on the page. But we're not really using the bandwidth of this connection very effectively. What you want to see is a full pipe. You want to be maximally using your bandwidth throughout the entire path of the page load. The key stats for this test, the bytes didn't change. Again, we're not making any content changes. We're just rolling out H2. Start render also didn't really change a whole lot. This is expected. Most of the H2 benefits come after start render. It's when you're downloading the rest of the resources on the page, all the CSS, all the JS, all the images. But the most important thing here, the speed index, which is a measurement of how fast the page was perceived to load, that went down by 15%. So the takeaway here is that you're going to expect a decent improvement on typical sites from H2. Maybe it'll be 15% for you. Maybe it'll be 40%. It really depends on the content of your page and how optimized it is. One of the nice things about H2 is that it's going to have a way bigger impact on sites that are poorly optimized. If a site isn't spreading images, it's not combining its CSS files and JS files, that's where H2 really shines, because you have a ton of HTTP requests that are very expensive under H1, but are very cheap under H2. Another common question people ask is, what about TLS? What about HTTPS? After a lot of deliberation, the spec authors decided they weren't going to require it, but some implementations do require it. Those implementations, in this case, are browsers, right? So Firefox and Chrome do require HTTPS for an H2 connection. Now, if you're disappointed by this because of the overhead of TLS, you're worried about that extra round trip, I would suggest checking out istlsfastyet.com. This is a great resource that talks about how to optimize TLS and how to really make that overhead as minimal as possible. And again, remember, in an H2 world, we have one connection and one TLS negotiation. So you're only going to pay that cost once per page load. And it's potentially even lower because of things like TLS session resumption and session tickets. You can make second and third page loads on the same site even cheaper than the first page load. So really, TLS doesn't add that much overhead. And I think having that extra security is a benefit. So far, it's kind of been all puppies and rainbows with H2. So there are a few things that people criticize it for that I'd like to just quickly cover. One thing you'll hear a lot is it was rushed and we wanted more out of the protocol. If you're going to do a major version bump of HTTP, why don't we put more things into it, right? Why do we only get kind of these four main benefits of multiplexing, header compression, request prioritization, and server push, right? Some people want a lot more. My attitude on this is that something good now is better than something perfect in 5 years. Now, this is something people will argue about till their faces turn blue, but I think that the reality is that small incremental changes are a better way to deploy things on the web. If you had a giant BC break or giant protocol that was harder to get rolled out, then people wouldn't deploy it. And also, we're going to get a ton of benefits today by rolling out H2 that we wouldn't get if we were waiting for it to be perfect and full of other stuff. The second thing that you'll hear about is why does it require TLS? And as we just saw, the spec doesn't require it, but some browsers do. As I said, I think security is a good thing, but there's also another really important benefit to having a requirement for TLS. And that is if there's an intermediary proxy that doesn't speak H2, if that content's not encrypted, it might actually have some problems with dealing with that content. But if you encrypt the content, then the intermediary can't see into the protocol and it can't actually break, like it can't have problems. So it actually does improve the rollout because you're encrypting all of that content, and then all an intermediary proxy can do is just pass it along because it can't view the content itself. So the bottom line here is that haters are going to hate, but by and large, people are pretty happy with HTTP2. All right, let's briefly talk about implementation. So web servers have pretty good support. Most of the major web servers have support with a plugin. The exception here that you'll notice that's pretty popular is IIS. Support apparently is on the way there in Windows 10, but currently you can see Apache, Nginx, Big IP, load balancers all support HTTP2/SPDY version 3.1. And you'll notice here Apache has mod SPDY and Nginx has a SPDY extension. These are going to get renamed, but today they are called mod SPDY and SPDY respectively, and they're really just the same thing as H2. SPDY 3.1 is not super different from the finalized spec. So you can turn that on today and you're going to get pretty much all the same benefits. If you happen to be running IIS, you can always set up a Nginx box ahead of it to sort of proxy the traffic through it and get that benefit without needing IIS to have H2 support. If you terminate your TCP connections at the edge through your CDN, you may also be wondering about CDN support. This table is a little more sparse, not quite as good, but a couple of major CDNs have support, Akamai, Cloudflare, MaxCDN, and more are adding it in the near future. Since that spec is finalized in the near future, since it has been finalized, we're going to start seeing a lot of these CDNs roll it out very, very soon. Now, finally, a lot of people ask, what about supporting both clients? Right? So what if you have some H1 clients and some H2 clients? What optimizations are OK to keep, and what optimizations should I stop? I think the bottom line is that if you're already combining CSS files and JS files, that's fine. I wouldn't undo that. If you're already spreading images, that's fine. I wouldn't undo that either. There's no need to add this, in my opinion, but I think if you're already doing it, it's OK. One other benefit of combining CSS even under an H2 world is that you're gzipping these files, right? They're text files. So the larger the file is, the better the gzip compression ratio gets because the dictionary gets better. So you think about like combining a bunch of JS files into one file, you're going to get better minification ratios and you're going to get better gzip ratios. So even under an H2 world, you may still want to combine those files or at least see what the differences are on the compression ratios. Sprites, not much of a benefit there, just not really worth doing in an H2 world. There are some things you want to stop. Domain sharding actually hurts H2 connections because you're making those extra connections. So I think if you're rolling out H2 today, just completely cut out domain sharding. And then again, with inlining content, in most cases, inlining content doesn't buy you that much. And in an H2 world, you want the browser to be able to cache that content. So I really think you should skip that and ideally just serve those as actual requests. And that could be data URIs, that could be small CSS files, et cetera. So again, I want to call out that there's global support is about 80% here. So if you do roll out H2, the concern about H1 clients that don't support it isn't that big of a deal because the servers are always going to auto-upgrade clients that do support it, and they're going to be perfectly happy to serve H1 to clients that don't support it, and that's going to very, very quickly be the minority of your traffic. Now, granted, this is a global number. Depending on where your site operates, you might be above or below this number, but you can at least check it out. It's going to be pretty solid. All right, quickly wrapping up. So my takeaways I want you to have here is that H2 is here. It's fast, it's supported, and really you should just go implement it. Thank you. We do have about 5 minutes for questions. So, yeah?
So let's say that you've got an app that's got about 500 JavaScript files.
Mm-hmm.
And you've been aggregating them together for one, and you're doing caching and everything like that. With HTTP 2.0, the only benefit of doing that now is because of compression algorithms might be able to compress that data.
Yeah, so the question was, if you have 500 JS files, you've previously been compiling them into one file, one bundle you're sending down to H1. In H2, the only benefit is compression ratios. I mean, so that's kind of true. There's still some header overhead, which is very, very low. If you have 500 files, you're still going to have a little bit of header overhead because the URIs are unique. So 500 is a lot of requests. You're still probably going to see a benefit from combining them, especially because I would imagine the compression dictionary will actually be a pretty big win over 500 very small files versus one large file. But that's something you could try out. It's certainly not going to hurt you to have one bundle. The sort of trade-off there is if you have one bundle and you're changing it all the time, you're going to blow that cache like every day, right? So you have to kind of think of this trade-off of like how often are these files being changed versus how much of a benefit am I getting from this compression dictionary. So yep, all the typical like cache control headers, that's all going to work. It really just comes down to, if you're versioning your file with like a hash of the contents, or you're versioning it with like a timestamp, and you're changing that every day, you're going to be blowing that cache every day, right? So one thing that people will typically do is they'll take their big bundles, like jQuery and whatever, Angular, whatever you're using, and make that one bundle, and then have your stuff that's changing rapidly a separate bundle, so then you can cache them separately. Yeah. What about WebSockets? So WebSockets, I'm not super familiar with that. That's like using one connection as well, so it's sort of a separate entity than H2. Do you need it? You don't need it, no. That's a separate thing. You can run SPDY without WebSockets. They're sort of like completely separate implementations and protocols. Yeah. Yeah.
The only other thing I need to do to implement this is just use a web server that supports it.
Yeah, so that's why we didn't talk a lot about implementation, but it's actually very, very easy. With Apache, you basically just install mod SPDY and like turn it on, and just like it goes. So there's no content changes on your site necessary. There's no real implementation details. Even Nginx, the latest versions of Nginx, is automatically compiled in by default. So you basically just like turn it on in the config. So it's very, very easy to implement. The real challenge is like when you roll out your site, you want to make sure nothing's breaking. Etsy, we tried to turn this on for our internal stuff. We had an F5 load balancer, and we uncovered bugs as we were rolling it out. It's like still one of those things where a lot of the appliances and sort of less popular web servers and less popular software implementations do have bugs in them still. So you want to be a little bit careful with that. But something like the Apache mod SPDY module and the Nginx one are pretty well tested. And that's another really important thing to point out is that since SPDY v3 was this test bed for H2, even though H2 was very, very recently like finalized, it's still very well tested. It's been in production for a long, long time. So it's a really robust protocol. Yeah.
So you actually just talked about what I was going to ask earlier, which is you said Nginx does support SPDY right now.
Yep.
And I'm wondering, in your experience, when you have something like reverse proxy in front of, let's say, a couple of backends,
Mm-hmm.
you have your TLS that ends there, it ends at Nginx, and you have backends that may or may not support SPDY themselves. How do you handle that? Like, do you have the ones that do support it actually do connect to the reverse proxy?
Yeah, so the question is if you have a reverse proxy that supports H2 to the client, and then you have a bunch of backends, some of which do support it, some of which don't support it, how does that work? That should work perfectly fine, and really all you care about is from your proxy to the client. That's the connection that really matters. If you're talking about your proxy to your backend, there's probably super low latency there, and having a mixed H1, H2 connection field there doesn't really matter. That's all going to be very, very fast. It's really about sending it over the longer link to the client. So yeah, that's a perfectly reasonable thing to do. Yep.
For the remaining 20%, is there some sort of way to make a fallback so that it goes back to HTTP?
Yeah. So the question was, with 80% support, what about the other 20%? what happens to them. So all the modules like mod SPDY and the Nginx module, they will automatically detect if the client supports H2 and then just serve them H1 if they don't. So that's not something you have to handle. That's all going to be done by the web server for you. So it'll all work. It's just not going to break. Yeah.
Do you have your CDN matrix? Because like Akamai supports it.
Yep.
Does that mean if you have static assets that are served through Akamai, it's going to be HTTP2 or it's not?
It's opt-in. So yeah, I'll show this. So Akamai, you can see there's that opt-in tag. So if you have an Akamai account, you basically just, it might be in the UI right now, or you might just like call them up and just say, I want to turn on H2, and they'll just like flip a button and it'll be on for your static content. So that is certainly a very good and easy way to test it out. You basically have your root domain served from origin on your www domain, and you have a static content domain which has all your images in CSS and JS, and you serve that over HTTP2 through your CDN, and all that's on one domain, and it's just separate from your base domain. That's still not optimal because you're paying that extra DNS lookup and extra connection for that static content domain, but it's certainly a low impact way to try it out without having to deal with your basic like dynamic content. I think we're actually out of time, so I'll take one more question if anybody has one, and then we'll wrap it up. No? All right, well, thank you very much.